Okay, so welcome to lecture number 17. Let's more or less go from where we left off last time. So the objective in the last lecture was to use transformers. So let me use this. So use transformers to do operator learning, right? So I'm not going to reiterate what operator learning is. We have been looking at that for last 10 lectures or so. But the idea of why we wanted to use transformers is to scale, right? So this is the keyword here is scaling. So you want to scale with respect to data and with respect to model size, so overall with respect to compute. So that's the objective now, right? And we started in last lecture by giving you some ideas of how this works. And this was the, let's say, summary slide, summary box. So your input or input embedding doesn't really matter. Let's say that this is your input function, v of x, because we can interpret all these operations in terms of operators, right? Means not in terms just of matrices or of functions between vectors and vectors, but as operators between functions and functions. So we needed some positional encoding in order to, because otherwise everything is permutation invariant. And then essentially there were only three elements, three essential elements. There is MLPs, which were here. There are norms. So this was the layer norm that I just described in the last lecture. And the most important element, of course, is attention, right? And this is where, let's use this perhaps. So this is the element that was the most important, and that's sort of, in some sense, a new element when it comes to transformers. And just to reiterate what that is, again, at the level of functions, even though everything can be done with respect to discrete quantities, functions on the grid, so what you get is that attention has this single head attention. Multi-head attention is just summing over all the heads. So you get this structure here. So essentially what you do is that it's sort of point-to-point connection, if you want to think of it that way, perhaps with putting a picture. So in other words, you have these points, you have this, what are called tokens or values at these points. So let's say that this is something like this. And then you have the same points again, because we want to indicate connections. And you can just imagine that this is your VK, this is your VJ, and so on. And what attention does is that it, in order to update the value at this point, you look at the sort of relative information that each of these guys throws to this point, right? So this one, this one, this one, so on. So everything is thrown out here. And then the idea is that you take a relative weightage of how important the information from all these points are, okay? And this relative weighting is done through a softmax, which is in the integral version, it is given by this term here. And in the discrete, the quadrature version is given by this classic formula here. So in some sense, attention is a very, very intuitive mechanism because it just takes into account correlations or relative contributions of different parts of the input to the output. That's the heuristic. And it is easily seen when you do this, means when you think of it as a kernel, because in contrast to FNO, CNO, and so on, where all the time, whenever we do the work at the level of functions, operators, we have to do some sort of kernel operations. So for FNO, CNO, we know that the kernel itself was translation invariant and it was sort of a fixed kernel. It was a learnable kernel. We infer the kernel from data, but during the inference, for instance, this is not the case, right? It's just something that has already been there. Here, on the other hand, because we take into account the relative contribution of each of these tokens, each of these points, then what you end up is some sort of a nonlinear data-dependent kernel. Okay, so perhaps I should use the word data-dependent. So this is why, in some sense, transformers has some desirable properties that you will see here. So this is the way to think of it, that instead of having a kernel that is inbuilt, that is something that we give using some prior knowledge. For instance, the inductive bias that is used here is translation invariance or equivariance, right? That's why we take this sort of X minus Y type kernel. On the other hand, here we have no such inbuilt implicit biases or inductive biases. What we have instead is that it has to learn it from the data. Okay, and we offer it a lot of scope to learn from the data because, as you can see, there are lots of all data points make a contribution. It could be that the nearby points make much larger contributions than the far off points. That's the structure of the data. In that case, you can imagine that you're slowly hinging towards this, right? Because here it gives more weightage to the neighborhood. Actually, it gives all the weightage to the neighborhood than to the others, right? But in some sense, you can see intuitively that if that is the case, if that there is more weightage to the neighborhood, all that it will do is that the attention, the relative the attention weights for the neighboring points, so let's say these 3 points, would be almost 100% and the rest fall off very, very quickly. So you can somehow recover this locality also from having this kind of a global structure. But of course, in some other problems, perhaps this is not the right kind of an inductive bias. Then it is able to leverage, it is able to sort of understand this and should be able to learn. So this is some, let's say, very rough heuristics into why, of course, it was proposed more from the perspective of language, where if you think in terms of language, attention makes a lot of sense, right? In vision and in PDEs, it's a little bit less, but if you think of it in terms of a nonlinear kernel, then of course the intuition becomes in some sense stronger. So this was the sort of the key element, right? This was the key element. And the rest were, of course, some details, because as you can imagine that the other elements were like point-wise operations, MLP, layer normalization, and in some sense, they are not the essence of attention. Essence of attention is really this, essence of a transformer is really this attention block here. Good, so now that seems all well and good, but there must be a caveat, right? The fact that we are allowed to be so general that we can interpret locality, we can interpret global information, so on, we should pay a price. And what is the price that we pay? Remember that I already alluded to it, that in order to compute these relative weights, we had to do another loop here, right? So we had to go again and then compute the attention weights by doing a, so we fix this point and then again we do a broadcast. So essentially all these points make a contribution and then you compute that. So here you have k operations, so k tokens, here you have k more tokens. So you have this quadratic complexity. And this is exactly what I wrote down here, that in terms of the number of tokens, the cost is actually quadratic. So the compute in the, even just one single inference, remember that with respect to machine learning algorithms, there are two distinct processes. There is inference and there is training. So inference is when you deploy your architecture, right? And this is during training, what you do is that you repeatedly loop over, keep on inferring through all the data set that you have, right? So there is a, so training, of course, is much more expensive, but these are not completely unrelated to each other, right? Because during training, you have lots and lots of inference rounds. So now how does the compute look like? So essentially, this can be computed. It's rather straightforward to compute. I could have gotten something wrong, but the key point here is that it's quadratic in the number of tokens. Okay, so this has serious implications. Of course, remember that we also have some input features, and this is the hidden dimension. So hidden dimension was here, right? So this Q, K, and so on, if you remember, the query, for instance, is a M times N matrix. So what you do is that you take information from N dimensions, and typically you lift it to N dimensions. The other way around. You start with N dimensions and you lift it to M dimensions. So you can think of M being much larger than N. Maybe perhaps not much larger, but certainly larger than N, because it's a lifting dimension. It's a Legion space in some sense. So this is, of course, also quadratic in the number of features, but that's less mild compared to the number of tokens. Why is that? Let us imagine that we are talking about, forget about the weather, but let us take a very, very simple situation. We have fluid flows, incompressible fluid flows. So Navier-Stokes equation. So our unknown in some sense is the velocity, v, and this has two components, the x and y component. And so in 2D, it has two components. So this means that n is equal to 2. Even if m was equal to 100, or let's say 10, okay? This is, I'm just putting some numbers here. Usually it's not 10, it's more closer to 100 than it is to 10, but let's say that it's 10. So this you can see is just 20. It could be 200. It does not really matter. Now, what is the number of tokens? So remember, the heuristic that we have now is that if you think of an image in 2D, so we have an image. So this is the domain. Then each point corresponds to a token, right? Because in each point, the point value at that point corresponds to a token. There are two channels. Let's forget the channel dimension because that is included here. But so there are how many points now in 2D? So it depends. Let's say that we do some, let's even take 128 squared, right? So 128 squared is 2 to the power, how much is that? So 2 to the 7, so 2 to the 14, right? 2 to the 14 is a very, very big number already. So that's the number of tokens, okay? K is 2 to the 14 because each of these points gets expanded into a line, right? So you have 2 to the 14 tokens. So what is the complexity now of a single inference run? It's 2 to the 28. So it is 20 times 2 to the 28. Now, 2 to the 28 is a very big number. I don't even want to imagine how big it is, right? Roughly speaking, it is 2 to the 28 is like 10 to the, it's 3. So 10 to the 9, it's more than a billion, right? So it's already more than a billion, which is a very, very, it's big. This is just in 2D at a low resolution. Now just scale the resolution up and just let's start doing some numbers. If you're in 3D and you're at 128 cubed, then all bets are off, right? Because now you can see that the number of tokens, K, is 2 to the 21, right? No, isn't that correct? 2 to the 7 cubed is 2 to the 21. And the number of parameters, the number of total number of the cost in terms of the number of tokens is 2 to the 42. And that is, you're talking about trillions already, right? So this is, even for the biggest machines that are available there, these are still forbidding numbers, okay? So it's okay because the point why transformers were very good was for text in the beginning. You only had text, and you know that text, spoken text or written text, this is not very rich information because this can be stored with a very few number of tokens. Usually there are these embeddings, byte pair, word piece, and so on. And these store it in very, very few. Even the whole of human knowledge as encapsulated in Wikipedia, for instance, is not that many tokens, in terms of tokens. But as soon as you come to images and as soon as you come to sort of scientific data sets, which are more closer to images and even videos, three-dimensional images and so on, you get into a problem. So this is the problem with transformers, right? Because they have this quadratic cost, and that can hit you hard in some cases. Of course, there is also a way out. And the point about transformers is that there is extreme parallelism. What does it mean? Parallelism means that different processes during computation can be chopped off, and this can be sent to different parts of the processor, different threads, different GPUs, whatnot, right? And in fact, it's very easy to calculate this, that there are exactly order of one sequential operations. Nothing depends on anything else. So in particular, if you think of the operations here, let's take the operations here because this is the expensive one, right? MLP and layer norm and so on. These are very, very easy operations. These are pointwise. There is nothing that is happening. As you can imagine here, for each of these points, or whether here, for each of these points, we could have computed things in parallel. There is no interaction between them, right? We could have taken the query, you would have applied it onto the vector, and we could have just done it for each of these points independently of each other. And similarly, all these operations are the only things that depend are similarly the computation of the keys, the computation of the values. These are all can be done independent of each other. Only when you take a dot product have you got to combine them, right? But that's not a very, dot product is an easy operation compared to the actual computation of this matrix vector products. And similarly, softmax can be computed. All the things that go into the softmax, these exponentials, they can be computed completely independently of each other, and there is one accumulation operation. So you can imagine that there's a lot of parallelization, and this is the reason why, even though the compute can be expensive, you can parallelize and you can extremely parallelize. And that's why transformers work so well, because you have this parallelization features that I explained. And also there is a concept of path length that I don't want to go into any details. It says that in the same round, you can go from any point to any point. So path length is how well are different parts of a computation connected to each other. We know in transformers, every point is connected to every other point, or every point including itself. So of course, there is a unit one path length. So it's very, very easy to leverage those facilities here. So the parallelism helps, but it doesn't help if you still have 100 trillion compute size, right? So there is a limit to it. So in 2D, potentially you could get away, but no one does that. Even for images, no one does that because you don't want this large computational volumes. So we need some sort of, that's why it's sort of attention, point-wise attention is would be considered still infeasible and perhaps unnecessary also because you don't need that kind of local information. After all, the difference between text and image or text and scientific data sets is that if you think of this room, for instance, and we are interested in temperature in this room, there's a much more regularity in the temperature in this room. There's a lot less variation between the temperature here and temperature here compared to, of course, you can argue compared to temperature here and far away, right? So there's a lot more regularity. So you could leverage those regularities. It's the same with an image. When I look at you guys, there is much more regularity than at a pixel level than it would be, for instance, when I'm talking, because each of the words that I say, there is no regularity as such. There are discrete events in some sense. So we are going to leverage those regularities that these data structures have in order to reduce the cost of computation. And this is what I'll try to do for the rest of the lecture today. Are there any questions about the computational aspects or what are the computational challenges of transformers? No, it's obvious. Good. Let's move on. So one possible solution, which is widely used in vision, because vision has exactly the same problems. Remember that the inputs are images, is what is called vision transforms. So this was actually proposed by mostly people sitting in Google at Zurich. And this is called vision transformers. And let me explain what it is, and then we can look at some of the details. So the idea is to use images as the main sort of concept here. So think of an image. So it's a poor drawing, but it will serve the purpose. And you can think of a domain, a computational domain, and you know that at the end of the day, things are discrete. So there's a bunch of points at which we are going to sample the solution, right? A bunch of points at which we have the image represented, something like this. Usually 128 squared, 256 squared, 512 squared, and so on. The idea, as I said, is to leverage regularity. The fact that locally things change slowly, but of course, if you accumulate these changes over global scales, spatial scales, then there'll be larger changes, right? So the idea behind these people who proposed vision transformers was very simple. That why don't we divide the domain or divide the image into what are called patches? So heuristically what it is actually very, very simple. Writing it down in formulas is a bit cumbersome, but so I divide it into blocks or patches. I've just done a very, very crude approximation of it, right? So instead of looking at these, how many points did I draw? 20 points. I just look at, in this case, 6 patches. This is just some numbers that I'm throwing here, right? So 6 patches. And the idea is that there is so little variation within the patch, there is so much of regularity within the patch, that I could essentially, instead of having these 4 pixel values, I could replace them with a single feature, a single attribute from the patch, or a single feature, single attribute from this patch, single attribute from this patch, and so on. So by dividing into patches, instead of having 20 potential tokens, I went down to 6 tokens. Of course, this process scales. Just imagine if I have a 128 squared image and each patch is 16 by 16. And this was typically what the original vision transformers paper resolved. Then instead of looking at 128 squared point values, I simply look at 128 divided by 16 squared, and that is 64 point values, right? So there's a dramatic reduction in the number of tokens. All that you leverage is the fact that neighborhood information is taken into account, that things don't vary dramatically within the neighborhood. As you'd expect also solutions. Yes, James.
Concept kind of reminds me of like multiple methods of it. Is there like some kind of
like fast multiple?
Yeah, for example.
Mm. Yeah, it's a very simple partition of unity type idea in some sense, right? Multipole is a bit more hierarchical. This is much simpler because for those who know, multiple methods or these are called tree methods anyway. So there is a hierarchy where you leverage the hierarchy. You don't use any such deep sort of, you could do it. You could also patch based on that kind of a featureization, but this is a much more naive way of doing it. Because you see that multipole would work very well if you have a lot of regularity, right? Then you can just cut off some parts here. Images and solutions to very complicated PDEs, they have some regularity, but they don't have that many. There are jumps and so on that probably it's just as well to do this. Okay. So let's try to look at some of the math. So the idea is very simple, right? That you just take this non-overlapping patches, and in each patch you aggregate the features of these nearby tokens, nearby points, let's say, and you form them into this so-called visual tokens. Okay. So each of these guys is a visual token. A visual token. It's like a word. Token is roughly a word in natural language processing. So it's like that. So the key point is this patch formation. Sorry. Let's use this. So this is patching, and I just explained what that is. By the way, I made a mistake here. H equal to W, just for simplicity. So all of this can be done with unequal sized images. There's nothing fancy here. So now you pick up patch size P by P. As I said, 16 by 16 was the default choice. In the numerical examples that I'll show you in the next lecture, we would use 4 by 4 because we expect that for solutions of PDEs, the patches have to be even smaller. But anyway, so you have n patches. So you can imagine that if H was 128 and P was 16, then this is a severe reduction. Okay, so instead of having 128 squared, which is 2 to the power 14 tokens, you'll only have 64 tokens, which is much easier to work with, right? And then the point is that this is so there could be a loss of information, right? So the loss of information could be from the fact that, okay, you're just cutting off the image into discrete points. And then, so what? Means you're losing information also. You're essentially taking averages, right? But what you do is that always in machine learning, you learn something. You learn some additional features. You say, okay, let me learn the best, roughly speaking. There's a heuristic, right? There's no guarantee that that heuristic is taken care of during the training process. But let me learn uh, instead of just taking an average of these 4 points, which is what I could have done, this is the easiest aggregation that I can do. Let me take a learnable sort of feature extraction. Okay. So what does it mean? Roughly speaking, is that you take weighted averages. You'll see when the operator version comes in the next slide. You take some sort of, roughly speaking, averages means with shared weights. So the patches are, so it's the same features that are being learned, the same types of features that have been learned across the different patches. And then, of course, each time you embed it into a latent dimension, plus some latent embeddings. There's always that, okay, we lose some information because we are taking into account the regularity, but perhaps we keep that information because we are projecting into a bigger space. This is always the trick, right? We also remember with the UNet architecture, this is what we did. We coarsened, we downsampled, but we increased the number of channels because there we could learn something. And remember that the sort of the increasing the number of channels would have been a very mild operation because this is a very mild thing to begin with, right? So even if I go from 20 to 120, it is nothing like the 2 to the power 42 numbers that we saw with the number of tokens. So this is what happens here. Again, the detail is not that important. So what you do is that you extract this local averages. So these are the local point values. They're just binned together into these objects, and then you embed them into a bigger space. So these are some learnable embeddings. So at the end of the day, instead of having an image, you have, and instead of taking every single pixel and laying it out as a very large vector, large sequence, what you do is that you do this in this clever manner. So each of this is the same embedding, as you can see. So that, as I said, the weights are shared. It's like a local average. So think of this V1, V2 as local averages, weighted learned averages. with the same features that are being extracted across each patch, for instance, right? So the advantage now is that we have exactly n tokens. We have reduced the computational complexity considerably. And at the same time, hopefully, by taking these learnable elements, we keep some of the information that is available. And these are the things that are fed into a transformer. So the transformer remains as before, that it is going to attend, but now what it is going to attend to is different. Earlier, it would have just attended every single point value. Now it is attending this learned local averages. Okay, so there is a subtle point here. And this sort of becomes very, very clear once. So at the end of the day, if you think of it heuristically, all that you are left with are these tokens. So I just bunch these things here and I have extracted them. Of course, the channel dimensions are different, right? So instead of just temperature, pressure, humidity, whatever, it has 20 different parameters which are supposedly learning some features that are lost while patchifying. Now, these are very, very simple heuristic in that sense. It can be written as operators, means this is exactly sort of justifying what I have just said, that you do this, you divide the domain into this non-overlapping equal patches. If possible, it need not be equal, but that's the simplest. Then you take weighted averages across each patch, and these weights are shared, right? And then finally, you sort of embed them into a latent dimension. So this is roughly what these formulas indicate. As I said, the emphasis is to aggregate information while at the same time keeping some of it through additional channels. Okay, so the heuristics is very simple. These are very, very easy to implement operations because all that you do is you just multiply right kind of matrices or tensors based on the right kind of embedding dimensions that you take. So is patchification clear? The mental image that you should always keep is this, that from this complicated image, you come to a simple sequence instead of coming to a much longer sequence that would have happened, right? Any questions about this? Yes.
Now we still need a positional embedding.
We'll absolutely need a positional embedding. You cannot, because now this, it is still, there is some information, there is some inductive bias. I will talk a little bit about it. In fact, that was the next slide, right? So, okay, let me get to it so that I discuss it. We still need to add positional embeddings because there is no sense of once you put these tokens, there's no reason why I just took them in one particular order, right? I could have just juggled them around and I would have gotten similar thing, right? So there's no sense of any kind of position in this process. So what do? How do we put position? We put learnable ones, just like I explained in the last lecture. Actually, it's very simple. So I just append. Now, instead of doing, last time I said the most general case is MLP, but in practice, people use just linear, very simple linear positional embeddings. So remember that this guy here, sorry. So each of these, so these are, so this is a vector, right? Each of them is, so there are n of these, capital N of these tokens. Each of them is, I probably made a mistake with the number of dimensions here, but maybe not. So each of this is an Rn vector. So these are new features. And then all that I do is I add an additional piece of information. I append to it an additional piece of information, which simply tells you what the location, where the position is, right? So roughly speaking, this here, which is a vector, which is a n cross n vector. So each of these components, so for instance, E pos 1 is essentially telling me what is the position of EV1. E pos 2 is telling me what is the position of EV2 and so on and so forth. Of course, there's a trivial way in which you can view it as an operator. That's not important. It simply tells you where the thing is inside the domain. Okay, inside the which patch does it belong to and so on, and what is the relative position of this patch. Good. So you always need position embeddings. You have the position embeddings. You have the new features, the patched features, and these are the ones that you feed into the transformer. So the with operator block, as you can see, is of the following form. Okay. So as you can see that you have, this is in 2D, you can do this in 3D also, you can, or 4D, any dimensions, you can make patches, but the algebra becomes complicated. That's why I explained it simply in 2D. Okay, so now you have your domain, computational domain, you have your input, which I'm assuming is a continuous function with C channels, and then it's a sequence of operators. So as you can imagine, the first step is to do the patch embeddings. So do the patch embeddings and the positional embeddings, and these are the new set of tokens, right? So this is roughly the set of tokens that I just extracted with the position embedding. So these tokens tell you where roughly where these things are, and then you throw them into attention, right? So you start by layer normalization. So you normalize, then you put some attention. I hope I didn't make a mistake here. I don't think so. And then you do a residual connection as before. And similarly, you repeat the process. You again take the output here. You do a, perhaps I should have, okay. It's roughly, don't I have a picture? No, but it's along the same lines as before. I should have had a picture, I'm sorry. So except that now you have the input embedding is in terms of a patch. This is the patch formation. Okay, and then it's the, now the order of these things is reversed, you know. So the norm comes first and then its attention, norms come first and then its attention. And this is simply to do with how well gradients, this is empirically observed that in some cases, putting the norm before the attention is better. In some other cases, putting the norm after the attention is better. And this keeps on changing based on the architecture. So there is no sort of proper way to say which is good and which is bad, because this is, whether you normalize and attend or whether you attend and normalize, you should roughly be in the same order, right? But the difference now is that in terms of the gradient propagation, because one has to train these algorithms, there could be some marginal differences. So that's a detail. I just want to give you what people have done in this regard, right? So okay, where is it now? Here. So as you can see, so you start with your input. So let me write it down. So you have your input, then you do patch, then a layer norm, right? So patch, layer norm, then the multi-headed self-attention, right? And then the input plus the residual. This is your new input. And then this goes through so this is a plus. Then it goes through a layer norm again, then an MLP. So this is an MLP. And then again, another plus here. And this is your final output. So this is how it looks like, right? I should have drawn this before, but you get the sense. And you have to stack several of the, yes. Is that correct? Let's see. So what is V hat now? V hat is just the input of the patching. Oh yeah, of course. Yeah. I always make this mistake also. Last time there was a mistake, right? Okay, good. Because I prepare these things late at night and I'm myself not having the full concentration. But good, you're right. Of course, everything is done in terms of patches. So at the end of the day, you get features per patch. So the very final thing, you have to extract things at the level of the image. But that is a very, very simple upsampling operation, right? So you just have each patch and you have to get the local information to each point. So again, so reverse what you did when you did patch formation, right? So in terms of matrices, this is very straightforward. I think in the next tutorial, they are going to teach you guys how to code up a vision transformer. So you'll learn it there. So what is the computational complexity now? And then where do we stand vis-a-vis computational complexity? The point is that, again, I have given in terms of an image, but you can imagine in terms of a function defined on a grid, right? So the resolution is here. And the compute, just in terms of the number of tokens, right? I've forgotten the fact that you have so many channels and so many features and so on. Those are not important. The dominant cost is given by the number of tokens. So if you take a standard transformer, point-to-point transformer, then this would have been my cost, right? And just imagine for a 128 by 128 image, this is quite expensive, right? But now if you have patches, then this is much better. So let's do the math here. So you have 2 to the 7 times 2 to the 7 squared. So this would have been 2 to the 28, right? But now when we do the patches, so you have 2 to the 7. So, okay, there's the same number, 2 to the 28, but the patch was, how much did I say? 16, right? So 2 to the 4, so 2 to the 16. So this becomes much more manageable, right? So 2 to the 12 is a very, very mild number. So it's not a lot of compute. So of course, it really, so as you increase the patch size, it's very, very clear that the compute becomes better. However, there is a twist here, right? And what is the twist? As you increase the patch size, okay, you can take the whole image as one patch. So at the end of the day, each time you do patching, you lose information. You're trying to recover that information by adding additional channels and so on. But you can imagine that if I had a 4x4 patch, we would have much better representation of the function than I would have taken a 16x16 patch, right? So there is always this tussle, this push and pull, tug of war between computation and accuracy. Means you want the things to be computationally feasible, which would mean that you want large patches, but at the same time you want a reasonable amount of accuracy. So you can't have very, very large patches. So for some applications like in imaging and so on, it is okay because at the end of the day, a lot of imaging is about classification. You see, so you just look at the image and you identify boy or girl. In our case, it's only boys here, so it's very, very easy, right? But men or women. But then you could have so in the classroom, of course. And then this is a very, very easy classification. It doesn't require a lot of detailed information about the face and so on. However, if there was a much more quantitative question being asked, like what would be the temperature given a certain amount of pressure, then can we really go to 16x16 patches or 32x32 patches? It becomes harder and harder, right? So it depends on the question that is being asked. So for most imaging applications, 16x16 is a very good patch size. But just empirically, you can imagine that if you want to do temperature calculations or structural strength calculations and so on, 16x16 is not so good. And we have to reduce the patch sizes to 4x4 or 8x8. And then again, the computation scales up because just by taking 4x4, I would have gotten another factor of 64 here. And that's a big number, you see? So this is, in some sense, doesn't scale for the applications that we have. So what do you do when you have relatively smaller patch sizes? We have another trick up the sleeve, and this is the one that seems to, at the moment, work the best. Let me just briefly describe it because I have 5 more minutes, and in next lecture, we sort of focus much more. It's a very interesting and a very natural idea, very recent in imaging, of course. All these ideas come from vision. And then we just reiterate and recycle them for our purposes. So this is called windowed attention. There are many, many ideas. Means there's axial attention, there is shifted attention, there are all kinds of long attention, hierarchical attention. But I think this is intuitively the simplest in some sense. And the idea is that you go to another level of complexity or another level of representation and work at that level of representation. This was introduced approximately 2-3 years ago by 2.5 years ago, perhaps, by some people from Microsoft in Beijing. And the idea is windowed attention. What does it mean? So remember that this was my original image. It's some sort of a castle, as you can see. It's not it's just at the level of an image, and that's good enough to explain. And then what you do is that each of these boxes here are patches. Okay? So each of these boxes here are patches. And we have whatever number of patches that are there. And when you do attention, all that we do is that we take, let's say we fix a patch here, let's say this patch, and then we compute the attention weights from all the other patches, right? We calculate the value here, we calculate the value here. Of course, we calculate the neighboring values and so on and so forth. And this, particularly if you have small enough patch sizes, which is what we want to do, then this can be expensive. And this is what I just explained, that this can be expensive. The idea of these people was very simple, that instead of doing attention over each patch to patch, instead of point to point, we went to patch to patch. Now they say, let's not do attention over patch to patch, because that's the expensive part, right? Because that's where it's quadratic. Let's do it over windows. So these windows are an additional layer, an additional level of description of detail, which is that you divide the image. In addition to the patches, you divide them into these kind of windows. The windows are much bigger, so each window contains quite a few patches. These can be equally distributed. In practice, they always are, because the more equal things are, the easier it is to call things from memory, to cache things, and so on. So you make it as simple as possible at the level of computation. Although in principle you could make this differently sized and so on, but each of them contains quite a few number of tokens. Let's say in this particular case, each of these windows contains 16 patches. Okay, each of them contains 16 patches, and attention is only happening inside the window. What does it mean? That when I am computing the update for this particular point here, I know that I have to compute attention, right? But to compute attention, I have to compute the attention with respect. Earlier, I did it with respect to all these points, this point here, as well as this point here. Now I don't need to do this. I don't need to do this. I don't need to do this. I just look at the nearby points. So the global information is lost. I'm just looking at local information, like I would do in a CNN, for instance, right? In a CNN, I would do exactly the same. I'm taking local information and I'm using that to update, okay? So of course, this makes things much easier because now instead of attending to all the other 63 tokens, I'm only attending to the 15 other, or including itself. So 16 tokens instead of 64 tokens, right? So, and similarly here, in order to compute attention, I just compute over all the neighboring points here. I compute over all the neighboring points here. So this is not global anymore, it is local. So we all just imagine in terms of kernels, this kernel has a support inside the window, right? And that of course reduces computation considerably because now attention is not happening across the entire domain. It's only happening across these windows, and M is the number of windows. M is the number of windows. And of course, the number of windows is much less than the number of patches. So of course, if I have 20 windows, 20 squared is nothing compared to the total number of patches. Then of course, the question that you'll ask is, okay, then how am I ever going to learn anything about, then what's the difference between this and essentially CNN? Because at least in a CNN, you're sliding across your window is sliding. So you are sort of intuitively taking care of other points. How do we do that? And the idea is, and this is what I finish with. Okay, I'll talk about it. The idea, just to give you an idea, is that across each layer, you shift the window. Just like, so, okay. So across, intuitively, it's very simple. Let's say that I was never attending to these 2 points. But now if I shift the window in the next layer, then what happens is that this point and this point are exactly in the same window. And if I shift it in the next layer, then 2 other points will be in the same window and so on. So intuitively, by shifting the window across layers, in each layer, you still keep it constant, but across, no one tells me that the window size should be fixed. Across layers, you're going to stride over the whole image, okay? And this is sort of the key feature by which one can attend to all the, let's say, all parts, representative parts of the image, right? But perhaps this requires a little bit more detail, which we will do in the next lecture. But you can think that where these ideas come from, the ideas are rather simple. And by doing this striding, you reduce the path length across tokens. So you do have a global information propagation by just harnessing the fact that you're striding the windows. Okay, simple and a very elegant idea that works quite well. Okay, with this, let's stop here. Today was again this short lecture, not very effective because half the time I'm reminding what I did in the last lecture, but but yeah. So, and next Wednesday, there's a holiday. We are all supposed to stop working on that day because of workers' rights, but but then we are back on the 6th, right? Oh no, 3rd, sorry. Okay, ciao then.